Our Earth is a dynamic and ever-changing planet. While it may appear static and unchanging to us in our daily lives, beneath the surface lies a hidden world of immense geological activity. This activity is driven by a fascinating process known as plate tectonics, a theory that revolutionized our understanding of Earth's geology. Plate tectonics explains how the Earth's outer layer, or lithosphere, is broken into several large and small plates that constantly move and interact with each other. These interactions are responsible for shaping the Earth's surface, creating mountains, volcanoes, earthquakes, and other geological wonders. The theory of plate tectonics emerged in the mid-20th century, building upon earlier observations of continental drift. Scientists began to realize that the continents were not fixed in place but were slowly moving across the Earth's surface over millions of years. This groundbreaking idea provided a unifying framework for understanding a wide range of geological phenomena, from the distribution of earthquakes and volcanoes to the formation of mountain ranges and ocean basins. To understand plate tectonics, we must first delve into the Earth's internal structure. Our planet is not a homogeneous sphere but is instead composed of distinct layers, each with its unique properties. At the Earth's center lies the inner core, a solid ball of iron and nickel subjected to immense pressure and temperatures hotter than the surface of the sun. Surrounding the inner core is the outer core, a liquid layer of iron and nickel that flows and generates Earth's magnetic field. Above the core lies the mantle, the thickest layer of the Earth. The mantle is primarily composed of silicate rocks rich in iron and magnesium. Unlike the brittle crust, the mantle behaves like a very viscous fluid over long periods due to the intense heat and pressure. This fluidity is crucial for plate tectonics, as it allows the plates to move slowly on top of the mantle. The outermost layer of the Earth is the crust, a thin and rigid shell that varies in thickness. There are two types of crust: oceanic crust, which is thinner and denser, and continental crust, which is thicker and less dense. The Earth's lithosphere, comprising the crust and the uppermost part of the mantle, is broken into numerous pieces called tectonic plates. These plates, like giant rafts on a slowly churning sea, are in constant motion, albeit at a pace that is barely perceptible on a human timescale. The movement of these plates is driven by the heat escaping from the Earth's interior. This heat creates convection currents in the mantle, similar to the currents in a pot of boiling water. As the hot mantle material rises, it drags the overlying plates along with it. These plates can move toward each other, away from each other, or slide past one another. These interactions at plate boundaries are responsible for the most dramatic geological events on Earth, such as earthquakes, volcanic eruptions, and the formation of mountain ranges. The study of plate tectonics is essential for understanding the history of our planet and the ongoing processes that shape its surface. Divergent boundaries occur where tectonic plates move apart from each other. This separation allows molten rock from the mantle, known as magma, to rise and erupt at the surface, creating new oceanic crust. As new crust is generated, it pushes the older crust away from the boundary, causing the seafloor to spread. This process, known as seafloor spreading, is the engine that drives the movement of continents and the opening and closing of ocean basins over geological time. One of the most striking examples of a divergent boundary is the Mid-Atlantic Ridge, a vast underwater mountain range that stretches for thousands of kilometers down the center of the Atlantic Ocean. At the crest of this ridge, magma erupts from the mantle, creating new seafloor and pushing the North American and Eurasian plates apart. This process, ongoing for millions of years, has gradually widened the Atlantic Ocean and continues to do so at a rate of about 2.5 centimeters per year, roughly the same speed that your fingernails grow. Section 5. Convergent boundaries, clashes, and upheavals. In contrast to divergent boundaries where plates move apart, convergent boundaries are marked by the collision of tectonic plates. These collisions are formidable geological events that release tremendous amounts of energy, resulting in some of the most dramatic and destructive phenomena on Earth. When two plates collide, the denser plate is typically forced beneath the other, a process known as subduction. Subduction zones are often associated with powerful earthquakes, volcanic eruptions, and the formation of deep ocean trenches. One of the most well-known examples of a convergent boundary is the Ring of Fire surrounding the Pacific Ocean. This zone is characterized by frequent earthquakes and volcanic eruptions due to the subduction of the Pacific Plate beneath surrounding plates. The Andes Mountains in South America also result from the convergence of the Nazca Plate and the South American Plate. As the Nazca Plate subducts beneath the South American Plate, it pushes the continental crust upward, creating the towering peaks of the Andes. Section 6. Transform boundaries, sideswiping plates. Unlike divergent and convergent boundaries where plates move apart or collide, transform boundaries are characterized by plates sliding horizontally past each other. Since there is no creation or destruction of crust at these boundaries, they are not typically associated with volcanic activity. However, the immense friction between the plates can cause them to lock together, building up stress over time. When this stress exceeds the strength of the rocks, it is released in the form of powerful earthquakes. The San Andreas Fault in California is a prime example of a transform boundary. This fault marks the boundary between the Pacific Plate and the North American Plate, which are sliding past each other in a northwest-southeast direction. The movement along this fault is responsible for the frequent earthquakes that plague California, including the devastating 1906 San Francisco earthquake. Section 7. Evidence for plate tectonics. The theory of plate tectonics is supported by a wealth of evidence from various fields of geology, geophysics, and paleontology. One compelling piece of evidence comes from the study of fossils. Identical fossil species have been found on continents now separated by vast oceans, suggesting that these continents were once connected. For example, the discovery of fossils of the Mesosaurus, a freshwater reptile in both South America and Africa, provided strong evidence for the existence of the supercontinent Pangaea, which began to break apart about 200 million years ago. Another line of evidence comes from the study of paleomagnetism, the record of Earth's magnetic field preserved in rocks. As magma cools and solidifies, magnetic minerals within the rock align themselves with the Earth's magnetic field, preserving a record of the field's direction at the time of formation. Studies of paleomagnetism have revealed a pattern of magnetic stripes on the ocean floor that are symmetrical about mid-ocean ridges. These stripes provide compelling evidence for sea floor spreading, as they indicate that new crust is generated at the ridges and spreads outward over time. Seismic data obtained from studying earthquakes provides further support for plate tectonics. The vast majority of earthquakes occur along plate boundaries, where the movement of plates generates stress and strain in the Earth's crust. By mapping the distribution of earthquakes, scientists can delineate the boundaries of tectonic plates and understand the types of forces acting upon them. Section 8. The importance of plate tectonics. The theory of plate tectonics is a cornerstone of modern geology, providing a unifying framework for understanding a wide range of geological processes. It helps us explain the distribution of earthquakes and volcanoes, the formation of mountain ranges and ocean basins, and the evolution of Earth's continents and climate over millions of years. Understanding plate tectonics is crucial for assessing natural hazards, such as earthquakes and volcanic eruptions, and for exploring for natural resources such as oil and gas deposits, which are often associated with specific geological structures. Moreover, plate tectonics plays a vital role in Earth's climate system. The movement of continents influences ocean currents and wind patterns, which in turn affect global temperature and precipitation patterns. Volcanic eruptions, often associated with plate boundaries, release greenhouse gases into the atmosphere, influencing Earth's climate over both short and long timescales. Section 9. Conclusion. A dynamic planet in constant motion. The theory of plate tectonics has revolutionized our understanding of Earth as a dynamic and ever-changing planet. The continuous movement of tectonic plates shapes Earth's surface, creating mountains, volcanoes, earthquakes, and other geological wonders. From the depths of the oceans to the heights of the Himalayas, plate tectonics is the driving force behind the geological processes that have shaped our planet over billions of years. By studying plate tectonics, we gain valuable insights into Earth's history, its present state, and its future evolution. The Earth is not a static sphere, but a dynamic planet in constant motion, driven by the relentless forces of plate tectonics. If you enjoyed this journey through Earth's dynamic dance, make sure to subscribe to my channel for more fascinating insights into our planet's wonders.